It's a spectacular sight and it had tourists on the hop. Mount Etna erupting in dramatic fashion, the world's most active volcano putting on quite the show.
Mount Etna has stood tall for thousands of years, breathing fire and shaping Sicily. But now, something strange is happening beneath it. The whole volcano is slowly moving, inch by inch, toward the sea. This is not an eruption. It's something even harder to stop. Engineers worry about pressure, gravity, water, and time together. And with the mountain constantly drifting, the coastline could change forever. If a giant volcano can slide like this, what does it mean for the land and the people nearby? We are about to find out why one of Earth's most famous volcanoes is slipping into the sea. Foundations in motion. Why Etna's flank is unstable. Mount Etna stands as one of Europe's most active and most watched volcanoes. Its summit rises above the island of Sicily, a familiar sight against the Mediterranean sky. But what lies beneath that great height is not as solid as it looks on the surface. In fact, the ground under Etna's southeastern flank is slowly creeping toward the sea. This movement isn't new. Scientists have known for decades that Etna's eastern slopes are unstable. But only in recent years have researchers begun to understand what is really driving that slow slide and what it means for the future. The southeastern flank of Mount Etna is not resting on firm, rigid rock. Instead, much of the volcano sits on softer, weaker layers, ancient sediments, and marine deposits that were laid down long before Etna rose. These sediments act almost like a slippery floor beneath a heavy object. As Etna has grown larger over thousands of years, its own weight has pushed down on these weak layers. Over time, this weight and pressure have caused the volcano's base to deform and shift. Satellite measurements and ground observations have shown that the entire edifice of Mount Etna, not just a small section of it, is moving downslope toward the Ionian Sea at a measurable rate. Researchers have estimated that on average this movement is a few centimeters per year, roughly the speed at which fingernails grow. It might seem slow, but over decades and centuries, even these small shifts can add up to significant changes in the shape and stability of the volcano. For many years, scientists debated what was causing this movement. Some thought it was mostly the result of magma pushing outward from below, inflating the volcano and forcing its sides to spread. This type of internal pressure can and does change the volcano's shape during eruptions and intrusive events. But recent data have shown that this is only part of the story. When movement was measured far from the summit, especially under the sea, it became clear that magma alone could not explain the pattern. In fact, deformation increased with distance from the volcanic center, suggesting the dominant force was something external. The key factor, scientists now say, is gravity. Etna's southeastern flank is perched on a slope of weak sediments that are easily compressed and sheared. Over long periods, the force of gravity slowly drags the flank outward and downward toward the sea. This process is known as gravitational sliding, and it appears to be the main cause of the volcano's slow motion. This idea of gravitational sliding changes how scientists view the volcano's instability. It means that the movement is not just a side effect of eruptions or magma pressure, but a fundamental outcome of Etna's position on sloping, weak ground. The volcano has accumulated enormous weight over time, and gravity is simply acting on that mass. Even when the volcano is not erupting, its flank continues to creep seawards, driven by this persistent force. High-resolution measurements of ground motion from satellites, GPS stations, and now even underwater sensors have given researchers a more complete picture of this process. On land, instruments show steady outward movement. Offshore, the newly installed GEOC seafloor geodetic network has for the first time detected similar motion beneath the waves, confirming that the sliding extends into the Ionian Sea. This means that the entire southeastern flank, both above and below water, is part of the same unstable system. As data accumulate over time, this view has grown stronger, helping researchers refine models of deformation and risk. The southeastern flank of Etna is home to towns, infrastructure, and thousands of people. Even a slow, gradual shift changes stress on faults and can interact with eruptive activity and earthquakes. In the event that small movements become larger or more rapid, the consequences could be serious. But today, even though the measured rate of movement remains slow, there are signs that a sudden collapse might be imminent. How scientists measured the slide. For years, much of the evidence that Mount Etna's southeastern flank was moving toward the sea came from measurements taken on land, but one question remained unanswered. What was happening underwater along the part of the volcano that extends beneath the Ionian Sea? Because satellites cannot see through the ocean, scientists lacked direct measurements of the submerged flank. That changed with a remarkable scientific achievement: the first ever underwater geodetic monitoring of a volcano's submerged flank. In the spring of 2016, a team of researchers from Geomar Helmholtz Center for Ocean Research in Kiel, Germany, and collaborators from Kiel University and the Italian Istituto Nazionale di Geofisica e Vulcanologia set out to solve this mystery. They used a research ship named Poseidon to place a network of acoustic monitoring devices on the seafloor near the submerged southeastern flank of Mount Etna. These devices, called transponders, were anchored across a fault line that separates the stable part of the slope from the moving sector. Each transponder did a simple but vital job. It sent and received acoustic signals to and from its neighbors every 90 minutes. Because the speed of sound in seawater is known, scientists could calculate the exact distance between the instruments at each moment. As long as the distances stayed the same, the slope remained still. But when those distances changed, it meant the seafloor itself had shifted. Over the course of about 15 months, the transponders recorded changes in position beneath the waves. The breakthrough came in May 2017, when the system detected a clear movement event. Over a period of 8 days, the distances between transponders on opposite sides of the fault changed measurably. The submarine slope had slipped about 4 centimeters toward the sea and had also dropped vertically by about 1 centimeter. This kind of motion is known as a slow slip event, like a very gradual earthquake that happens without the shaking typical of regular quakes. What made this discovery so important was that it provided the first direct evidence of true horizontal movement underwater. Before this, scientists could only infer motion based on data from above the sea's surface. Now, for the first time, they could see that the flank was moving both on land and beneath the sea, and that the motion was part of the same overall process. When researchers compared the underwater measurements with satellite and ground data, they found a striking match in the direction and amount of movement. Another key insight from the underwater measurements was the role of gravity in driving this motion. If magma rising inside the volcano were the main cause of flank movement, scientists would expect the greatest deformation to occur near the summit and on the landward side, where magma pressures are strongest. But in the underwater data, the movement was clear far from the summit, suggesting that something else must be at work: gravity. This interpretation aligns with research on other coastal and island volcanoes where similar processes have been proposed. The distinction also affects how scientists interpret past collapses and landslides in the geological record. Large ancient debris fields offshore and the shape of the Valle del Bovi on land indicate that parts of Etna have failed catastrophically in the distant past. Those events may have been triggered by combinations of internal and external forces, but the fundamental weakness created by gravity-driven sliding would have set the stage. Understanding gravity's role in the present helps scientists model how stress builds and how different triggers might interact with an already unstable flank. The underwater measurements also revealed that flank motion at Mount Etna is not constant at a single speed. The movement can happen in bursts, slow slip events that last days or weeks, separated by longer periods of relatively quiet motion. This pattern is similar to the slow slip events detected on land through GPS and satellite data. It appears that the underwater flank participates in the same episodic motion, responding to the complex interplay between gravitational stress and internal volcanic forces. Because the instruments were spread across a fault line, the data provided more than just a simple indication that motion was occurring. They allowed scientists to measure both horizontal and vertical displacement, giving a fuller picture of how the slope was deforming. This is crucial for hazard assessment because the direction and style of movement can influence how stress accumulates in the volcano's structure and how a larger collapse might unfold in the future. The success of the GOC network also opened a new chapter for volcanic monitoring. Before this project, seafloor geodetic monitoring had been used mostly in subduction zones to study tectonic plate motion. Applying this technology to an active volcanic flank was a major step forward. It demonstrated that scientists can study submarine portions of unstable terrain in real time, which has implications for other coastal volcanoes around the world. Despite the advances, the underwater measurements have limits. The network operated for just over a year, and while the data collected were groundbreaking, they represent a snapshot in time. To understand longer trends, scientists need continuous monitoring over many years or decades. Even so, the data gathered so far have already reshaped scientific understanding and provided direct proof of submerged flank motion that was once theoretical. The deployment of underwater acoustic sensors was a milestone in volcanology. It confirmed that Mount Etna's southeastern flank is not only sliding on land, it is sliding under the sea too. And this motion is measurable, persistent, and part of a larger process that challenges old assumptions about how volcanoes behave. As tools improve and longer records accumulate, scientists will continue refining their models and watching the subtle dance between Earth, sea, and mountain that unfolds beneath the Ionian waves. Gravity versus magma. Mount Etna has a long and complex history of both active eruptions and catastrophic collapses. While the volcano is best known for its frequent lava flows and eruptions, it has also experienced massive landslides and flank collapses in the past. These events, which occurred tens of thousands of years ago, left behind visible scars on the landscape. These ancient collapses remind us that Mount Etna is not just an erupting volcano, but also a massive, slowly moving mountain that has undergone dramatic shifts in its past, continuously informing the way scientists think about Etna's future stability. The most significant of these past collapses occurred roughly 20,000 to 30,000 years ago, when parts of Etna's eastern flank suddenly slid into the Ionian Sea. Evidence of these massive landslides can be seen in the form of huge debris fields that now rest on the ocean floor. These underwater remnants are the remains of rock, ash, and soil that were once part of the volcanic structure. They were displaced by the sudden and dramatic failure of the volcano's southeastern side. When large sections of Etna's steep slopes became unstable, they broke away and slid into the sea, creating one of the largest landslides ever recorded in volcanic history. These past failures have been crucial for understanding the risks associated with Mount Etna's ongoing movement. Unlike many other volcanoes, Etna sits on a weak foundation of marine sediments, which are easily displaced. The volcano's steep slopes and the gravitational forces acting on the mass make it highly susceptible to sliding. When magma builds up and pressure increases, the volcano's fragile flanks may be pushed to the edge, but even without an eruption, the weight of the volcano itself can be enough to trigger collapse. This risk is compounded by the ongoing sliding of the southeastern flank toward the sea. While the possibility of a catastrophic collapse similar to those in the past may seem alarming, scientists believe that such an event is unlikely to happen suddenly or without warning. Instead of a sudden catastrophic failure, scientists expect that Etna's flank will continue to move in phases over the coming years. This slow-motion process could lead to smaller collapses at higher elevations, followed by more gradual shifts closer to the sea. Even these smaller failures, which might be triggered by volcanic eruptions or earthquakes, could displace large amounts of material and create hazardous waves along nearby coastlines. However, they are unlikely to generate the kind of massive tsunami that would result from a complete collapse of the volcano's southeastern flank. The real challenge for scientists is predicting the timing and scale of these collapses. Unlike volcanic eruptions, which are often preceded by clear signs, such as increased gas emissions, tremors, and magma intrusions, G-gravitational collapses do not show the same predictable warning signals. The exact moment when a large portion of Etna's flank might fail is still beyond reach. In other words, although there are no signs of an imminent collapse, scientists remain cautious, because once the process begins, it will be difficult to stop. To mitigate the risk, scientists continue to monitor Etna with a vast network of instruments. The ANGV Observatory in Catania, Italy, operates a comprehensive system that tracks ground deformation, seismic activity, and gas emissions in real time. The data from these tools are combined to create detailed models that help scientists predict the potential for future collapses. If the flank begins to accelerate, or if new signs of instability emerge, these models can help authorities prepare for potential hazards, such as local tsunamis or landslides that might threaten coastal areas. Though the chances of a catastrophic collapse are low in the near term, the potential risks remain. Etna's past collapses demonstrate that volcanic slopes can fail when the right conditions align, even without the presence of magma. The combination of weak sediments, steep slopes, and ongoing gravitational forces means that Etna will continue to move slowly toward the sea. If the right triggers occur at the right time, the volcano's flank could experience accelerated sliding. This would pose a danger to local communities and infrastructure along the coast. However, scientists will be watching closely, monitoring future risks. Mount Etna is not just an iconic volcano. It is also one of the most closely watched natural systems on Earth. Scientists in Italy and around the world have installed a vast network of instruments to monitor every subtle shift of this massive mountain. From high-precision GPS stations on land to satellites in orbit and even specialized sensors on the seafloor, researchers are tracking how Etna's southeastern flank moves, how it deforms, and how its internal forces interact with the pull of gravity. This continuous stream of data is essential for understanding the volcano's long-term behavior and for assessing the risks it poses to the millions of people living nearby. But even with all this technology, there is still uncertainty. Knowing what is happening is one thing. Knowing exactly when something dangerous might occur is another. These limits are why scientists speak cautiously about risk and why they continue to refine both monitoring and hazard models. The first layer of monitoring comes from the ground itself. A dense network of global navigation satellite system, GNSS stations, more commonly known as GPS, surrounds Mount Etna. These stations record movements of the volcano's surface with millimeter-level precision. When the southeastern flank shifts even slightly, these instruments detect the change. By combining data from dozens of stations, scientists can map how different parts of the volcano move in relation to one another. Satellites play a complementary role. Using a technique called INSAR, or interferometric synthetic aperture radar, orbiting spacecraft send radar pulses down to Earth and measure how the signals change when they bounce back. By comparing radar images taken days, weeks, or months apart, scientists can see shifts on the volcano's slopes that are invisible to the naked eye. When paired with ground-based GPS data, INSAR provides a three-dimensional view of how the flank moves over time, adding important context to what might otherwise look like random changes. There's also the deployment of the GOCE, Seafloor Geodetic Monitoring Network. Since radio waves don't travel well in water, satellites cannot measure motion below the surface, but sound does. By sending acoustic signals between these transponders and measuring how long they take to travel, researchers were able to detect even tiny changes in distance. This was how researchers were able to record the first direct measurement of underwater flank movement, confirming that the slide extends from land into the deepest parts of the mountain's foundation. Together, these technologies create a near-continuous picture of Etna's behavior. They reveal slow background motion, driven primarily by gravity, punctuated by short-term accelerations often associated with volcanic activity or small earthquakes. Scientists have learned that the underlying trend of outward motion is more consistent with gravitational sliding. If magma were the main driver, the largest movement would be closest to the magma chamber. Instead, movement increases toward the coast and offshore, pointing clearly to gravitational influence. Despite the unusual detail of this monitoring, scientists still face significant uncertainty when it comes to prediction of future events. There are no cues that help scientists to know in advance due to the way a gravitational collapse behaves. It may accelerate gradually over a period of time. Alternatively, it might be triggered suddenly by an external stressor, such as a large earthquake or significant rainfall, neither of which directly causes collapse. This makes precise prediction extremely difficult, even with the most advanced monitoring systems available. One of the hardest questions scientists receive is, could the flank collapse suddenly and cause widespread damage? The short answer is that it cannot be ruled out. For example, geological evidence shows that at least one large landslide emanated from Etna's flanks roughly 8,000 years ago, possibly generating significant waves in the Mediterranean. But those events happened over timescales much longer than human lifetimes. However, scientists emphasize that smaller stage failures are more likely than a sudden, total collapse. What makes Etna compelling to scientists is not just its eruptions, but its ongoing subtle shifts, its persistent motion toward the sea, and the way it challenges long-held assumptions about volcanic behavior. The mountain's slow slide is a natural process that unfolds over years and centuries. Understanding it requires patience, precision, and continuous observation. And while uncertainty always remains, the knowledge gained through these efforts brings clarity to a situation that might otherwise seem baffling, and ensures that we are watching carefully should the story change.